Black holes have been some of the universe's most enigmatic and intriguing objects for decades, fascinating both the general public and scientists themselves. Now, top theoretical physicist Michio Kaku has stunned the world of science with a daring and jaw-dropping revelation: we might finally have cracked what is contained within a black hole. This is no incremental breakthrough in astrophysics. It revolutionizes our concept of space, time, and the very nature of reality itself. The advance is focused around a new theoretical framework of black hole interiors that merges the concepts of quantum mechanics and Einstein's general relativity theory. Black holes have classically been defined as spaces with such gravity that nothing, not even light, can get out. In their center, this object is supposed to contain a singularity, an infinitely dense point where the laws of physics cease to apply. For decades, this singularity has been one of the most mysterious and elusive concepts in science, a dark realm outside observation or experimentation. But Kaku's new announcement indicates that the enigma is at last beginning to unravel. The center of this breakthrough is a radical hypothesis based on string theory and quantum information theory. Kaku and his colleagues have been developing quantum gravity models trying to bridge the macroscopic spacetime fabric with the probabilistic laws of the quantum realm. With the use of cutting-edge simulations and fresh data from gravitational wave detectors and the Event Horizon Telescope, they've advanced a breathtaking alternative to the standard singularity model. Rather than a region of infinite compression, the inside of a black hole could be something called a fuzzball. The fuzzball idea, which comes from string theory, takes the place of the singularity with a closely grouped, knotted bunch of vibrating strings, the building blocks of matter and energy in the universe. From string theory comes the idea that the various vibrational modes of the strings are responsible for all observed particles and forces. If Kaku is right, then the heart of a black hole is not an unexplained void but a densely packed ball of quantum information stabilized by gravity but not succumbing to a singularity. Such a radical change would mean that black holes are not termini of physics but portals to the understanding of the quantum fabric of the universe itself. The consequences are mind-boggling. One reason is that the fuzzball model resolves the so-called black hole information paradox, one of the longest-running issues in physics. Quantum mechanics holds that information regarding a physical system can never actually be destroyed. However, according to the old-fashioned picture of black holes, all information that goes into a black hole gets destroyed by the singularity. This conflict has confounded physicists for decades. The new theory, however, proposes that information is preserved either on the event horizon or encoded within the fuzzball itself, thus aligning with quantum principles and bringing us closer to a unified theory of everything. One of the most exciting consequences of this theory is that it fundamentally changes our perception of what a black hole is. No more shall we see it as an intergalactic vacuum cleaner, a morbid beast that consumes everything in its wake. Rather, it could be something altogether more advanced, a supercomputer processor of sorts, even an interstellar storage unit. If we could someday decipher the data locked inside a black hole, we might in theory piece together the history of everything it has eaten: star systems, planetary debris, or even civilizations lost to history. While the notion remains far from practical application, it alters our philosophical perception of black holes. No longer are they annihilators but rather recorders of cosmic history. This understanding also adds new significance to theories of the multiverse. If black holes harbor curled-up dimensions or domains where quantum principles hold sway, then every black hole might be a portal to another universe or an isolated division of a grander multiversal complex. Kaku's research has rekindled serious academic debate over wormholes and Einstein-Rosen bridges, once a subject of science fiction fantasies. If the inside of a black hole is now not a singularity but a quantum-dense construct, then the idea of traveling through black holes isn't as impossible as it was thought to be. Indeed, recent simulations have hinted that, under some conditions, the energy limits needed to make a wormhole stable might be lower than thought. If that is accurate, it would suggest that theoretical black hole travel is not a mathematical oddity but a feasible technological benchmark far in the future. Some physicists now suggest that signals, even quantum information, might flow through such tunnels, which would make new interstellar communication and physics frontiers available. The technology that made these observations possible is another breakthrough. Gravitational wave astronomy has permitted researchers to sense the disturbance caused by colliding black holes and black hole mergers. These waves contain precious information regarding the mass, spin, and possibly even the internal composition of black holes. Simultaneously, the Event Horizon Telescope gave us the first ever images of a black hole's event horizon, capturing the shadowy outline of these cosmic giants. Kaku's team synthesized these diverse data streams, applying advanced quantum simulations to visualize what might be happening beyond the event horizon. Their findings included gravitational echoes, faint reverberations after black hole mergers that suggest exotic behaviors of space and time near and inside the event horizon. These echoes defied the explanation of traditional singularity models. Rather, they are seen to fit precisely with the string theory and fuzzball hypothesis predictions. While indirect, the evidence presents a powerful picture of black holes as vibrant quantum objects rather than featureless voids. Such findings have deep philosophical implications as well. The notion that black holes encode and store information beyond the event horizon means that nothing in the universe is ever lost. It opposes our concepts of finality, death, and vanishing, proposing instead that everything leaves a mark, a record, on the universe. This is a profoundly transformative vision. Stars that died eons ago, planets that have been destroyed, and even sentient beings who once gazed at the stars could, in some way, still exist, embedded in the quantum design of black holes. Kaku's discovery makes us reimagine our connection to the universe. We are not just far-off observers, peering into space from a distance. We are part of a finely webbed, information-laden universe held together by quantum entanglement and gravitation structures. The possibilities for our concept of time are equally revolutionary. Time within a black hole does not function in ways we're familiar with. According to some theories, time becomes more spatial, static, and omnipresent, such that past, present, and future could exist together at the same time inside the black hole. If so, then the interior of a black hole may keep not just physical matter it devours, but each moment attached to that matter as well. This opens the very intriguing prospect that black holes may be able to unlock time travel, not fantasy, but theory based on quantum physics. In addition, this discovery gives new life to the centuries-long quest for a theory of everything, one single description of all physical forces and phenomena. The similarity between the concept of fuzzballs and string theory might prove to be the elusive bridge that at last unifies general relativity and quantum mechanics. These two cornerstones of contemporary physics have defied unification for decades, depicting wildly disparate worlds. But with black holes in the middle, we might have discovered a natural laboratory for unification. Perversely, the very bodies once regarded as stumbling blocks to advancement could turn out to be the solution. There's another consequence to take into account: Hawking radiation. This effect, found by Stephen Hawking, explains the way black holes leak out radiation and dissipate away over billions of years. Before, Hawking radiation was supposed to contain no information, that is, the contents of the black hole were gone forever. But if fuzzballs store data internally, then this radiation might be affected. In effect, black holes might not dissolve into nothingness, they might emit their secrets into the cosmos. In their dying breaths, they might emit whispers of information about their hidden contents as they fade away. This idea defies centuries of traditional scientific dividing lines between the knowable and the unknowable. The event horizon has represented a one-way curtain, an absolute edge beyond which information could not travel back. Kaku's model turns that on its head. The event horizon is not a wall, but a veil, a surface that might be cracked open. The black hole is no longer so much an abyss as a vault. Its secrets are concealed, but not inaccessible. This theoretical breakthrough might lead to new technologies, equipment designed to decode Hawking radiation patterns or search the nuances of gravitational wave signals. If successful, these equipment may usher in a new era of astronomical discovery, enabling us to observe cosmic events not by being there, but by listening for the echoes that they send out. New generations of space telescopes and gravitational detectors could soon be tuned expressly to search for these concealed signatures, extending our observation capabilities further still. The cultural significance of this finding cannot be overemphasized. Artists, writers, and philosophers will inevitably be attracted to its symbolic meaning. In a world where even the darkest chasms are occupied by structure and memory, black holes evolve from metaphors of destruction to symbols of resilience. They defy our dreads of oblivion with the allure of preservation. The idea that knowledge, matter, and even consciousness itself may be able to survive in some way within these cosmic motors addresses human nature's greatest desire: to be remembered, to be chronicled, to be comprehended. Michio Kaku's news does more than move us forward in science, it raises our cosmic tale. It informs us that the universe is possibly more benevolent than we had imagined, more ordered, more connected, and more eternal. Black holes, which were once dreaded and mischaracterized, are now unveiled as keepers of memory, doors to the universe's innermost secrets, and perhaps even portals to realms beyond our understanding. If you enjoyed this video, could you please like and subscribe to our channel for more revolutionary updates? And we'd love to hear from you. What do you think about the secrets that black holes could hold? Does Kaku's theory change the game? Let us know in the comments below. Thanks for watching, and as always, keep looking up.